Well, now we're working our way onto a theorem similar to the intermediate value theorem, but it's more an intermediate value property that holds for derivatives. But before we get there, we need this following lemma. It says if f is a differentiable function on the closed interval ab, and the derivative is not equal to 0 for any x in the open interval ab, then either the derivative of x is greater than or equal to 0 on the entire domain of AB, or it's less than or equal to 0 on the closed bounded interval AB. So let's take a look at the proof. We will use the theorem 4.9 again. By theorem 4.9, the first part of that, f prime of x not equal to 0 for all x in AB implies that f is a one-to-one function. Remember what this means? This says that the function, it's either, if it's increasing at one point, it is never going to level out and become 0 or negative. It's just going to continue increasing. Or it could continually decrease. But what does one-to-one tell us? One-to-one tells us that f is monotone. Actually, it tells us that it's strictly monotone. So it's either strictly increasing or strictly decreasing. This is by theorem 3.19. One-to-one implies strictly monotone. So what we'll do is assume f is strictly increasing. And I will leave off the comment that I frequently put in brackets. If f is strictly decreasing, the proof would be nearly identical, or very, very similar. Thus, for all x and y in the closed bounded interval AB, where x and y are not equal to each other, so I'll say with x not equal to y, we see that f of x minus f of y over x minus y, let's see, what can we say about that? It's an increasing function, so let's just say that x is less than y. If x is less than y on the x-axis, and if f of x is less than that, we've got an increasing function, f of x minus f of y would give us a negative number, over x minus y would give us a negative number as well. So we'd have a negative over a negative, so it's greater than 0. And if you reverse the two, you'll end up getting the same thing. We'll get a positive number over a positive number. So we're guaranteed that that fraction, which looks a lot like the derivative. As a matter of fact, we would get the derivative if we take the limit as y approaches x. So, actually, we're almost done here. This implies that the derivative is greater than or equal to 0. F prime of x greater than or equal to 0. That's the end of the proof. And why does it say greater than or equal rather than greater than? Well, we're taking a limit. These are positive numbers. And even though every x and y give us a positive number, a limit could actually be 0. So this could, as we take the limit, this could turn into 0. So f prime of x is greater than or equal to 0.